seems like you answered your question. If you actually need like 5 minutes, we can.
Oh no, that's okay. That's right. That's good. Perfect. Thank you. All right. So let's get started. I have to erase this. So before the break, we were just talking about this ultralight dark matter, and we'd put together this picture of it as this classical coherent field. Then I said, and we saw how big it was. And then I said, okay, how do we look for it? And we took as an example that first simplest example of that electron mass coupling. And I said, okay, that will cause, if I have an electron in my lab here, that will cause any electron, every electron that's sitting right here, right in the lab or in my hands, if it's bathed, if that is the dark matter of the universe, and it's filling all space here, passing through us, then all of our electrons, their masses are wiggling, that tiny little bit. Not much, but they're all wiggling a little bit, right? Okay, so that's kind of our first, it's a good canonical example of this kind of signal of ultralight dark matter that we want to look for. So how can we look for it? So now let me give you our first example of a very high precision experiment that could look for such a thing, okay? So this is not much. This is a tiny oscillation in the electron mass, but we're good at playing with electrons. And in particular, if the electron mass is oscillating, well, we know that the electron mass, it's responsible for many things, most of what we see around us probably. But in particular, the electron mass sets the scale of atomic energy splittings, right? And we are very good at doing atomic physics by now. Atomic physics is one of the things we humans do the most precisely, right? So maybe we can use that. Maybe we can use the fact that changing the electron mass would change the energy splittings of all atoms, right? Remember your hydrogen atom formulas or whatever. In fact, there's no other dimensionful scale in the problem, really. The proton mass is so heavy it doesn't really count. So more or less, the electron mass is the only dimensional scale in the problem. The energy splittings of all atoms must be, that's the dimensional scale. It must be set by the electron mass. Then some alphas, right? Okay, so how can we use that? Well, as you may know, one of the most precise things we build are atomic clocks. So here, for example, is a picture of an atomic clock. I don't expect you to take much from this picture other than they're complicated. I believe, by the way, I think this is a picture from Junyi's lab, Junyi's group, which is just down in the neighboring building here at Chilla. One of the world's best atomic clocks. They have a fantastic group here. Something to note, however, here is the fractional frequency stability, the precision, essentially, of an atomic clock versus year, okay? The blue are the old atomic clocks, but in particular, these red are the optical atomic clocks. That's what I'll be telling you about. You can see it's pretty amazing. They've gotten better really fast. And they're now, by the way, so this strontium clock at 10 to the minus 18 is not even the best anymore. I just don't have the most up-to-date plot. It's already down to 10 to the minus 19, or even maybe a little better. So in other words, the atomic clock can keep time accurately. They usually say, in 10 to the 19 seconds, longer than the age of the universe, you only lose 1 second. Of course, atomic clocks don't actually last 10 to the 19 seconds. That's a bit false, but the fractional stability is that impressive. 19 digits, right? It's pretty amazing. It's definitely a feat, okay? So that's really good, 10 to the minus 19. I mean, that's a number to keep in mind, right? That's pretty good even compared to these small numbers, right? So if you remember 10 to the minus 19, right, then when you see small numbers like this, you might think, aha, wait, maybe I can use atomic clocks, okay? You can see, by the way, that these optical clocks have been improving about an order of magnitude in sensitivity or so every few years, which is really an amazingly rapid rate of progress. And I would say, from my somewhat outsider's perspective, but from talking to the people who build these, that the technology definitely does not seem to be done yet. It doesn't seem like we're reaching the limits of the technology. In other words, we can see clear things to work on. We can see clear technological advances, which we think we should be able to make, that will take us even some orders of magnitude farther. Okay? And in fact, just as an aside, if there is time at the very end of my 4 lectures, I want to talk about something which isn't ultralight dark matter detection, but is very dear to my heart, which is gravitational wave detection. In fact, I'm going to try to make the analogy between gravitational wave detection and ultralight dark matter detection. As I've said, they're actually pretty similar. But in the end, if there's a little time, I'll tell you about some ideas we had using atomic clocks to try to detect gravitational waves, because they are some of the most precise things people make. And this is something we're relying on as we're currently attempting to build first iteration of our atomic gravitational wave detector. So I sure hope they'll get even better. Yes?
Would you mind just briefly reminding us how the optical atomic clocks work?
Excellent. Absolutely. That was what I was going to do next.
Oh, cool.
Absolutely. I will not tell you how this works. Okay? I'll instead give you my very crude theorist cartoon of how an atomic clock works. Yes?
Very specific question. Why did the precision increase on the blue line when there was the redefinition of the SI second?
Oh, I think, good question. So that was before my time. I'm not quite that old, but I believe that was when it's not that improved the precision, it's that was when they switched and defined the SI second in terms of atomic clocks. So that was a historically big event. And people are still, I believe, pushing to define the second in terms of optical clocks. Although I think they haven't decided whether it's strontium or ytterbium or who's going to win. If you walk down the hall, that would be a major, big, controversial question. Fun. I'll show you where the sensitivities come from, and that will maybe answer better what the limitations are. But let me say that's why I was careful in what I said. So when I give talks about my gravitational wave, our gravitational wave detector idea based on atomic clocks, people often ask me how far can it go, because to detect gravitational waves, we're going to need to go farther. So I was careful when I said, I don't know, I won't answer fundamental limitations. I'm not going to go that far. I only want to project technology a few years into the future. It's hard enough to do. But we see no reason why we can't keep improving at least few more orders of magnitude. Let me stay at, even that is controversial enough, but let me stay with that. If I get a chance, I'll try to talk to you at the end about this technology a little more and how we want to push it to look for gravitational waves. Great. Okay. So she asked a great question. What is an atomic clock? How does that work? An atomic clock is really an atom interferometer. So this is I'll tell you about the general subject of atom interferometry. Okay. And in particular, my extremely crude theorist cartoon of how an atomic clock works. I take an atom, like strontium, for example, that has 2 energy levels, 1 and 2. Okay? Actually, it has a whole complex manifold of energy levels. I'll just pretend there's only 2. All right? I'll gloss over all the really complicated atomic physics that makes this work. But there's a lot more to be said. I can tell you more about this later if you're interested, or offline, after the lecture or something. But it's simple enough to just consider 2 levels that have some energy splitting delta E. Okay? And then let's say I take an atom. By the way, that sentence that I'm going to start this atom, I'm going to start it in state 1. That sentence already has multiple Nobel Prizes. Because what I actually need to do is grab the atom, hold on, and cool it, and trap it with laser cooling and electromagnetic trapping methods. That was an impressive, very impressive accomplishment of many people. Because I need that, if it was at thermal velocity, room temperature, it would just be flying away and uncontrollable and completely useless. I need to have this thing just sitting there. I don't want any of its motional degrees of freedom excited. I want it just doing what I want. I want it perfectly controlled. That's a tall order and took, like I said, a lot of people, a lot of work over many, many years. So I'll skip multiple Nobel Prizes here. And just imagine I start with the atom in state 1, the ground state, okay? And I'm holding it right here. All right? The magic happens when I apply something I'll call a beam splitter. If I get time, I'll tell you a little bit later how that's made. But in these optical atomic clocks, for example, it is a pulse of laser light. If you speak this language, it's a pi/2 pulse. If you don't worry about that. What it does, just accept what it does, it takes the wave function of the atom and splits it into a superposition of ground plus excited. Okay? So just assume I can do that for a second. The impressive atomic experimentalists have figured out how to do this. Okay? Some coherent superposition. Then I just wait a time t. Okay. What happens then? Well, the atom is still in a superposition of ground and excited, yes? Those are energy eigenstates when the laser is not on. So the waited time t with the laser off, nothing happening, the atom just sitting there. Except it's not quite 1 over root 2, 1 plus 2. What is it? What's the leading order of things that happen? The real answer in the real world is many things happen. But at this level of approximation, all I've told you is there's an energy splitting. So that's the leading order of things that happen, right? This state is a higher energy eigenstate than this one. It picks up a relative phase, yeah? That's it. So I just pick up an e to the I delta E times t, okay? Then all I do, let's do it this way, is apply the same beam splitter again. It's a linear thing. It's just a pulse of light. It acts on each part of the atom's wave function separately. So it does to 1 the same thing it did the last time. It splits it into 1 plus 2. Yeah? So in particular, it puts a 1 there and a 1 there. Yeah? It takes the part of the atom's wave function that was ground state and makes it, splits it into ground state plus excited state. So first, let me pause. Is that clear so far? Get out of the way. All right. And then it does essentially the same thing to 2. It also splits it into 1 plus 2. Except by unitarity, there's a minus sign. I won't put that in for you. You can do the little 2-level, 2x2 Hamiltonian if you want. Or you may have done it in quantum mechanics. But it does basically the same thing, except it puts a minus there, because it has to preserve unitarity. And that's it. OK? Is that clear so far? Questions so far? All right. This phase, that's the key thing in the atomic clock, in the atom interferometer, okay? I want to read out this phase. That's got a measurement of time in it. I'm trying to make a clock, right? So this is the second beam splitter. And hopefully you see the analogy with an interferometer, right? Like a laser interferometer, you put light through a beam splitter, it goes 2 different paths, and then you put it through another beam splitter and recombine it, yeah? So look what this did. This took an overall phase shift difference between the 2 halves of the wave function, which is unmeasurable, not interesting, yeah? And turned it into a number difference between the number of atoms in state 1 versus state 2. All right, is that clear? And the number I can measure. I can shine some other light resonant with some other transition and read out how many atoms in state 1, how many atoms in state 2. Okay? And those are called the 2 output ports of the interferometer. So this, fortunately I went over the board, this coefficient here, that gives me n1, the number in state 1. And this coefficient here gives me n2, the number of atoms in state 2, or the fraction of the atom's wave function in state 2. Mod squared, really, right? Okay? And so that's what I read out. These are the 2 output ports of the interferometer. A lot like when, a laser interferometer, you put it through the last beam splitter, and then you read out how much light went this way, how much light went that way. Yes?
So the beam splitter is acting on a whole bunch of atoms at the same time, or is it like sending atoms through?
Great question. You could do either one, and they have done either one. For now, I'm describing it even just as one single atom. And then, of course, in reality, I want to use more than one atom to get better sensitivity. But I'll treat each atom as completely independent. The way we would usually imagine doing it in the kinds of experiments I'm talking about, we would cool and trap a whole ensemble of atoms, usually about 1 million or so at a time, send them through this pulse sequence, send them through this atomic clock sequence, read them out, and then do it again. So that would be one way to think. But you don't even really have to worry about the other atoms. Each atom so far, from everything I've said so far, is completely independent. Yeah, good question. Yeah, so is this clear? Any other questions? Yes?
So it seems like you need to know that energy really precisely.
Good. Great. Excellent. So what does this tell us, I think is what you're asking. And we'll come to that. Exactly. Very good. So let me ask you, question for all of you. This is maybe a slightly trickier question. 3 questions. 1, what is the sensitivity to time? I want to measure time. So how small a little increment of time can I measure? Can I measure 10 to the minus 18 seconds or whatever? How small a little, what is my sensitivity to time? If, in the first case, I put 1 atom through this sequence. Just 1 atom, okay? In the second case, I put n atoms, okay? Actually, I'll have a third question, but let me not write it yet. So I want you to think about this. Is this question clear, though? So I can imagine I can measure how many atoms or what fraction of the wave function came into each of these 2 output ports. So how good a measurement am I going to get of time? Okay, is that question clear? Questions on the question? Okay, take a minute. This is, I think, a little trickier. Take a minute and chat take a few minutes and chat with the people next to you and see if you can figure it out.
Something like that.
Yeah, and you're thinking put the delta E as like the.
Yes?
I'm wondering, when you say like n atoms, is it like n separated atoms?
N totally independent atoms.
Okay.
So imagine, in fact, let me say, when I say n atoms, I mean n totally independent atoms. So you put 1 through, see which way it went, put the next one through, see which way it went, and so on. Yeah. And then in a second, I'll make them entangled. Mm-hmm. Say again, sorry?
1 over square root of n?
That's how it scales. Yes.
Oh, but like 1 million, it doesn't scale. There's nowhere close to this.
But what's setting the overall sensitivity? That's the question. So like even just one atom, what's the sensitivity in seconds of the atomic clock, let's say,
yeah,
for example?
yeah.
Okay?
There's some other precision.
Yeah. I'll tell you in just a second.
Yeah.
All right, as usual, let me interrupt you before you've really had time to think about it much. Sorry. But since we need time. So if I just put through one atom, right? Now, by the way, actually, if you really only put through one atom, which would be a silly thing to do, you never just do the experiment with trials like one if you can possibly avoid it. One atom, maybe you couldn't see anything at all. So really, I mean order 1 atoms, okay? But if I put through order 1 atoms, what could I possibly see? Well, I'm trying to measure this phase shift, yeah? And I've turned it into a number shift, a difference in the number in the 2 output ports. I'm trying to see that. But if I only put through 1 atom, what's my sensitivity? How well do I know like how big this fraction is and how big this fraction is? I really don't, right? I mean, at best, I kind of know dark and light. 1 or 0, right? I know like, was this very close to 1 and this very close to 0 or vice versa? That's my sensitivity, yeah? It's like order 1 to the number of atoms in the output port, right? And so the sensitivity to phase, to radians, is also order 1, right? I would need a order 1 radian. Delta E times T is a dimensionless number, right? Measured in radians. I would need order 1 radian shift to shift this number away from 1 significantly, right? Is that clear? Questions on that? Okay. So when you're evaluating atomic clocks or atomic interferometers, it's all about calculating the phase shift. That's your signal. So if I have just one atom, the smallest increment of time I can measure is when delta E times delta T is 1 radian, yeah? So delta T, the smallest increment of time I can measure, is 1 over delta E. That's it. Okay? Is that clear? That's the energy time uncertainty relation, if you like, yeah? And in optical atomic clocks, that's what one of the many things that differentiates the red dots from the blue dots. It's my crude theorist cartoon. What differentiates the red dots from the blue dots is, in optical atomic clocks, delta E is optical. It's about 1 eV, 1 electron volt. Okay? So this is then 1 over 1 electron volt, and if you use my h bars and c is equal 1 and convert it to seconds, 1 over electron volt in seconds, I got about 10 to the minus 15 seconds. Pretty darn good, yeah? For just one atom. Of course, you had to make the whole atomic clock, but still, that tells you how it got to be so precise, right? And why they defined the fundamental unit of time in terms of the in terms of the atomic clock. You've measured a time in terms of some fundamental microphysical parameter, right? Electron volts. This energy splitting in the atom, right? Which is very stable, very precise. We think stable, with a small asterisk that I'm coming to, right? But as far as the people who define the SI system, very stable, very precise, yeah? And gives you this awesome clock. Another way to say it is the tick rate of this clock is EV. It goes tick, 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 tick every 10 to the minus 15 seconds, right? The tick rate of this clock is 10 to the 15 hertz. Pretty damn good clock, right? You want a processor speed that's that fast or something. Okay? So I could see, in other words, the difference when I waited this time t, I could see, did I wait an extra femtosecond or one less femtosecond? That would make an entire radian phase shift difference. Black versus white, right? Atom is in ground or atom isn't excited. 10 to the minus 15 second waiting difference made that difference. Yes?
I'm sorry, I'm a little confused about how you see that signal, right? Like, at the end of the day, if you're sitting one atom, you're going to measure how you're excited.
Good.
And you're not off by 2 femtoseconds.
Great question, great question. Perfect. So absolutely. So first, I would never really put one atom through. I'd put n through, which is what we're coming to. And then I'd get some measure of how many went this way and how many went this way. So I think maybe that answers the first part of your question, that maybe 60% went here and 40% went here. So that would actually be measurable once I put more than one through, right? One, not a good experiment. But then the second part of your question is very interesting, yeah? Well, this is so damn precise. An extra couple of femtoseconds and the thing goes around by 2 pi, right? Absolutely, so it depends what you're looking for. I'm not particularly interested in timing how long this lecture takes to the femtosecond, yeah? That's not an interesting thing. I'm instead interested in tiny, tiny little signals as might be caused by ultralight dark matter. So I'm going to be interested in signals that cause less than a radian of phase shift, okay? By the way, however, as a general statement, there are some people who are interested in these big signals that cause many, many radians of phase shift. You can do that. There's many different protocols for doing that in general in an atom interferometer, even not just an atomic clock. There's people who use atom interferometers to measure a little g on Earth. It's one of the most precise ways to measure how fast an atom falls. And if you actually want like a number for little g at wherever you're at, 9.8, whatever, blah, 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 you need to measure many, many, many radians of phase shift. You do that by making a very imprecise atom interferometer, and then lock down the first digit, and then make a slightly more precise one, and lock down the next digit, and so on and so on and so on. It won't matter so much for me, but exactly that. That's what you do to map out when it's more than 2 pi radians. Yeah, great question. Yes.
Kind of related, you said the signal would be, for example, 60% in state 1 and 40% in state 2. Is that at some very precise time?
Absolutely, that's right. So if I waited an exact time t, no more, no less. Exactly, that's right. And of course, if I change the time t by even a femtosecond, it'll change radically how many are in which one.
So how do they know?
No, it's the other way around. Okay. This is the definition of time. Okay. This is the best humans can measure time. This is it. This is how many they put in. That's what defines time. The splitting of well, it's not currently an optical atomic clock, but let's pretend in the future it will be. Shortly, it probably will be. Maybe they'll pick strontium if they decide on the wars between the different groups. So it'll be the splitting of a strontium atom. Defines how many femtoseconds you put in. Exactly, because that's the most precise thing we can do. Yes?
So if we have a readout on this to hook it up to other systems, can electronics even respond that fast?
Right, no, not femtosecond. Electronics are usually, well, depends how you make the electronics, but usually no better than nanosecond.
How does the rest of your experiment even plug into this time frame?
Good, excellent. And you're not usually trying to time something to the femtosecond. It wasn't quite the way around. I'm not usually trying to time a single femtosecond. So you would just wait some actual amount of time, and then I've sent through a whole lot of atoms. They would tell me how long I've waited. And by the way, I won't discuss. You see how complicated the real atomic clock is. I won't get into any of the real complications. So you actually use this to feedback usually and stabilize your late. So you don't usually use the readout of this. You usually null it the same way LIGO has a dark port. If you don't know about this, don't worry about it. But as a technical aside, in case you know something, you'd usually actually null this out. So you would apply a phase to exactly cancel it. And that's your signal, actually, the phase you need to apply to exactly cancel it. And then you use that to stabilize the late. Anyway, there's a lot of steps between this and making a real clock. Absolutely. And in fact, I won't even be interested in a real clock. I'm just interested in this. This is the heart of the atomic clock. This is my crude theorist cartoon. I'm just interested in this heart of it because we're going to change it. I don't really want to measure time. I want to see dark matter or matter gravitational waves. So we'll change this up and use it to do those things. Great questions. Yes?
As an aside, which may be a tangent. So if you did want to measure a minimal amount of time, what would that be? How would you do that?
This one is gated. It's started and stopped by these beam splitters. These beam splitters, they take different amounts of time depending on your laser intensity. But they have to be started and stopped by electronics. So really, it's not going to be faster than a nanosecond or anything.
I don't mean specifically with atomic clocks. I just mean in general. What is the smallest amount of time you can measure?
Well, this is the best. The atomic clock is the best. That's why I'm talking about it. But it's the most sensitive measurement of time. The smallest of time would be how you define your thing that you're trying to measure. So almost always in a physics experiment, we're running it with electronics, computers. That's what runs everything in our physics experiments. So we have to flip open a shutter or pulse a laser or do whatever it is we're doing, record when the little blip, when the particle hit the tracker in the LHC, All that can be done to about, very roughly, nanoseconds. So that would be the smallest amount of time I can experimentally make in something like that. Of course, I can do other things that are smaller amounts of time. I made these pulse lasers. Anyway, It's a long question, but it'd be what did you want to measure, basically? Yes.
What is the answer or the correction to delta E? Like what order?
Oh, for the phase shift, you mean? Ah, that's a great question. We would say, I think what you're asking is, there's a shitload of noise sources for an atomic clock. What I've shown you, okay, so what I'm writing here is officially called shot noise. So I'm pretending this is the limit of the atomic clock, but it is not. But it's much easier to describe theoretically than all the other things that matter. And it's shot noise is just dependent on how many atoms I put through. But there's lots of other things. There's black body shifts to the phase shift, so the temperature of the surround does act on the atom. Any stray fields. There's a ton of stuff. That's why they have spent decades refining this. So I won't go into any of those noise sources, but they are very important. But one of the reasons I'm not going into them is they change depending on what you're doing with it. So when we use it to look for time varying states, so the atomic clock is, by measuring time as a DC, as a static thing, I'm just measuring time. I'm not looking for an oscillatory signal. It's almost always much easier to measure an oscillatory signal than a DC. To measure AC is much easier than DC usually. And many of those backgrounds of the atomic clock will not matter at all for a DC signal. Will not matter at all for an oscillating signal. They are DC backgrounds. So in many of the experiments we propose, you don't have to care about them at all, but you always have to care about this one. This is a fundamental limit, as someone was asking earlier. What are the fundamental limits? This is one. So that's why I'll do this one, but there's lots of other things which would read in as extra noise terms in this phase shift, yeah. Let me ask you now, what about this next question? If I put through n independent atoms, okay? So if I put through n independent atoms, you know that, well, it's shot noise. You know that I can measure, there's some expectation value, right? Maybe it was 60-40, right? So 60% of my atoms should have gone here, 40% should have gone here. But if I only put there 100 atoms, I don't expect exactly 60 and exactly 40, of course. Yeah, there's Poisson variations, root n fluctuations. So I can measure these to root n sensitivity, yeah? So there's some fluctuation on root n, divide by n, the sensitivity to delta t, then let's say roughly 1 over root n times the single atom sensitivity, which is 1 over delta E. Okay, so it gets better by 1 over root n the number of atoms I put through. That's how much better I can measure the phase shift or how many atoms went to each output port. Okay, is that clear? Okay. That's great because, as I said, if you can take 1,000,000 atoms per shot, that's a factor of 1,000 better per shot. And then ultimately, this is actually how many atoms I put through the whole experiment. If I'm looking for something like dark matter, I would integrate for months or years, right? They run LZ and CDMS for years. I'm making a direct detection experiment. I'll run it for years. Why not? So I could accumulate many, many atoms through here. Maybe 10 to the 6 atoms per shot, 10 to the 6, 1 shot per second. A year is 10 to the 7 seconds, if you let me dream as a theorist. Maybe that's a little too much. If I'm getting 10 to the 12, 10 to the 13 atoms, that's a lot of orders of magnitude, yeah? Then I get down to numbers, like 10 to the minus 21, 22. Those are like gravitational wave numbers. This is great. This is what you do. In principle, you might want to do even better. So I should say, is that clear? Questions on that? In principle, you might want to do even better. Let me ask you the following quick question. Which is, if instead I gave you a magical beam splitter, which didn't just split each atom from ground to 1 over root 2 ground plus excited, but instead it took the ensemble of n atoms all starting in the ground state. 1, 1, 1, 1, 1, n atoms all in the ground state, yeah? And now it entangled them. So I put them in 1 over root 2. They're all in ground, plus they're all in excited. Yeah, that's very different than this other beam splitter, right? The independent atom beam splitter, even if I put n atoms through, notice it started with they're all in 1, and it sent them into the first atom is in 1 plus 2. Oops. Oops. And the second atom is in 1 plus 2, and so on, yeah? So every atom was independent. So you see the difference between the two beam splitters? These are all completely independent atoms, and those are entangled. Is that clear? Okay, so now, if I gave you this magical beam splitter, what would be the sensitivity to time then? Take just a minute and talk with your partner and see if you can, or talk with the people next to you, see if you can figure it out.
Oh no, I mean like.
There's like, I'm debating between
Yeah. Yeah. This one. Yeah, you get this saved to the
out of curiosity, when you entangle things like this, I mean, you lose it on like the boson sensitivity, right? Okay. So it wasn't.
If it was like this, especially, yeah, as I'll say, yeah.
I think, okay, so if you wait, yeah. Yeah, very good. Then it's the same. And I would be like,
All right. As usual, I won't give you enough time. So what happens in this case? Okay. Well, in this case, I do the first beam splitter, yeah, and it splits it like this, so all the N atoms, they're in that state. So that was this first beam splitter here. I do this, now I keep going, I do the rest of the atomic clock, so I wait time t. That's the next thing I'm supposed to do, right? So let's wait time t. What happens if I wait time t? Well, there's still energy eigenstates, so not much happens. They're still all in ground or all in excited, yeah? But what phase do they have? There's n of them in the excited, yeah? In this part of the wave function, all n are in the excited. So it's e to the I n delta Et. Do you see that? That's the key step. That's the whole dream of entanglement here, okay? All right, so is that clear? All right, so yeah, so this state was n delta E higher energy than this state because it was n atoms, each was delta E. So you've evolved phase n times faster. I've brought up the tick rate of the clock by a factor of n. That's awesome. I apply this beam splitter again, measure the output ports, but now I've only got two output ports. Only two things can possibly have happened. All the atoms are in ground or all the atoms are excited. Yeah, I mean, you know, if I measure this wave function, I'm not going to get 60% of the atoms are in ground and 40% are in excited, right? These are correlated. These are entangled atoms, yeah? I either get they're all in ground or they're all in excited. Is that clear? So it's like I only get one measurement. It's black or white again. All one, all the other. So I get no root n on top of this, but I did get an n. Okay? So my time sensitivity is 1 over n delta E instead of root n delta E. Is that clear?
How many can you entangle?
Well, we can't do this. But this is the dream. Now you see why so many groups for so many years are trying to entangle. Atoms, light, same thing. I mean, this is good quantum mechanics. Works the same way with LIGO's lasers. This is squeezing, yeah? This is what they're doing in LIGO. They're actually already getting some sensitivity boost to their squeezing in LIGO. If this was n, though, number of atoms, let's say I put 1,000,000 atoms through, yeah? I would get a speed up over root n of 1,000. That would be awesome. Or LIGO has a 10 to the 19 photons per second go into LIGO, okay? That would be really good. They don't get a 10 to the 19, root 10 to the 19 boost to their sensitivity. So far, LIGO's demonstrated squeezing. I think it's about a factor of 2 boost to their sensitivity. The world's best squeezing that I'm aware of is done, I think, this is a few years old knowledge, but I believe it's in James Thompson's group here and in Mark Kasovich's group at Stanford. Those are the best ones I'm aware of. And they also demonstrate a little bit better than LIGO, factor of, I don't remember exactly, 3-ish or something. Boost to sensitivity. So like, trying to go the whole way to say, okay, what would really be honest to God, as they say, metrologically relevant squeezing, like squeezing that I could really use to do a real precision measurement. We're not at n. We're not at this yet. By the way, this is called the noon state because there's n atoms in state 1 and none in state 2, or there's none in state 1 and n in state 2, okay? So we're not even close to getting the noon state. Not even close, but it is a dream. They use lots of other much more complicated ways of squeezing that are some much, much more complicated wave function than this that I'm not going to try to talk about. Yes?
Could you imagine doing something similar-ish with like a both sides times condensate?
Often these atomic ensembles they use are cooled to BEC. Okay. So they often cool them all the way down to the ground state of the trap. Although if you don't do any fancy beam splitting, they remain independent. Just because they're in the same spatial wave function doesn't entangle them in any way. The magic is in the beam splitter. So you could do this with a BEC or not with a BEC.
Thanks.
Yeah.
So when you say there's a boost in sensitivity, so what are they actually doing? They're doing this sort of entanglement in conjunction with some other.
Well, they're not doing this, but they're doing, yeah, like James Thompson's group or Mark Kasovich's group. They do a certain, they take a small step towards the noon state. They do some amount of squeezing. Exactly. Maybe you're asking, it's a much more complicated state than this, though, and I'm not even going to try to describe it. By the way, so one, just in case you're curious about the name squeezing, you can see the origin of the name here. There's a number phase uncertainty relation, yeah, like energy time uncertainty relation or px. And so there's a number phase uncertainty relation, and here, when I did this beam splitter, they're all independent. So if I measured the state of all the atoms, I'd get about 50-50. And if I had 1,000,000 atoms, I'd get pretty darn close to 50-50, right? Because they're all independent draws. So not a whole lot of number uncertainty, yeah? There. But here, if I measure all the atoms, I get all in one or all in the other, maximal number uncertainty. That's better phase uncertainty. That's squeezing, okay? You've changed the error ellipses. Anyway, yes?
This is more of a point of curiosity, but was that factor of 3 what pushed the 10 to the minus 18 to 10 to the minus 19?
No, I don't think Junyi has got squeezing in his atomic clock, if I remember right, although don't quote me on that. They're still not demonstrating it in, like, it's more in they're doing it as proof of principle, demonstrator experiments. It's hard to do squeezing. LIGO has employed squeezing in the actual experiment. Good. Okay. Yes?
What if I have a multi-state system, like you just consider 2 states?
Yeah.
If I have multi-state, I have more measurement, maybe reduce the error or something?
So great question. Let me say, there are as many different ways to try to do squeezing and entanglement as there are different groups working on it. Well, more than there are different groups working on it. So let me, that's a great idea, but let me not say anything about it. I mean, I'm sure there have been whole summer schools run on entanglement in quantum systems. All right. Okay, so we've got so they can't actually do this, just to take away, but you see why they'd like to. All right, let me go back then. We've got a very precise measure, though anyway, the atomic clock, very precise measure of time. Or let me turn it around, right? That wasn't what I wasn't actually interested in a clock. Remember, right, at the end of last lecture, I want to look for ultralight dark matter. So remember, I wanted to look for this coupling of the dark matter field, coupling to E bar E, right? Wiggling the mass of the electron, right? Remember, the ME was going to be 511 keV plus some shift cosine M dark matter T, right? So I have this wiggling mass of the electron. That's going to wiggle all the atomic energy splittings. This delta E that I've got in my atomic clock, right? So boy, this looks like, here I called it a sensitivity to time, but I could have done it the other way and said, oh, this will be great. This is a really sensitive device to measure small shifts in delta E, right? Small shifts in delta E, I can happily wait whole seconds. That's not much to an experimentalist, yeah? If I wait a whole second, right, and I shift delta E fractionally by 10 to the minus 15, I get a whole radian phase shift. So that's great. Yeah, that's a very sensitive device for measuring small shifts in delta E. Yeah, so I can use the atomic clock to look for this. Yes, you agree? Oh, yes?
How are you going to measure the time?
Great, that was exactly what I was going. Well, wait, no, not so fast. I can't quite. By the way, I mean, this is, well, anyway. This is more or less how it goes when you think of a new idea. You're like, atomic clock, great. Oh, shit. Yeah, I have no idea what time it is. In fact, it's defined in terms of cycles of strontium or something, right? So if they define the second this way, they've actually defined out the dark matter, right? The second would truly be oscillating. We humans wouldn't know, and you'd have redefined it. So you see, right? I actually only measured delta E times t. We've called it the definition of the second, but anyway, let's go back to fundamental physics. I just measured delta E times t. So if I want to see a wiggling delta E, how on earth can I distinguish that from I just didn't make an exactly constant t, right? So my experiment would be I'd run the clock, and I'd run it for capital T equals 1 second, right? And if I knew for 100% certain that I ran it for exactly 1 second, 1 unit of time, and then I ran it again and again and again and again and again, over the days or weeks or months, I would see the phase shift oscillate, right? With a period of this ultralight dark matter, right? That would be great, except how on earth do I know that I'm always running it for exactly the same amount of time, right? In fact, the only way I could possibly, the best way to know would be to use an atomic clock to time that time, right? But if the atomic clock is the same thing, if I'm using a strontium atomic clock and another strontium atomic, so the way to do this experiment is to compare two atomic clocks, right? Is that clear? Do you see that? But it's still not going to work if I'm using the same kind of clock. So instead, I need to use two different atoms, or at least two different sets of levels that have different dependence on whatever parameter I'm interested in. So by the way, I've been talking about a shift of the electron mass, but the same thing applies if I couple to the fine structure constant, to the electron charge, or anything else that reads into this, okay? As I'll say in a second, there's a lot of different operators that would be visible in this kind of experiment. But I want, if I'm looking for a shift to the electron mass, I want two different levels that have different dependence on the electron mass. So for example, I claimed the only dimensional scale in the atomic structure was the electron mass, but of course that's not true. There is also the nucleus mass. There's the fine structure, whatever it is, right? There's the corrections that come from the non-infinite mass of the nucleus, me over m nucleus corrections. And so there are actually, these levels have somewhat different dependencies on delta ME, on ME. It's a somewhat subleading order, so you have to pay. You don't get the full sensitivity of the atomic clock, but it's pretty darn good. So maybe it'll be okay to pay a few orders of magnitude. Okay? So what you want to do, the experiment you want to do is compare atomic clocks run on two different level splittings. Could be with two different atoms, for example, that have different dependencies on ME, for example. Or if I'm looking to see a dark matter that is an alpha modulus that couples to the fine structure constant, different dependencies on alpha, right? The different energy splittings of atoms have different powers of alpha in them. Is that clear? Question on that? All right. So that's just exactly what people proposed. So here's a nice proposal for using atomic clocks to look for this kind of dark matter. You can see the paper up there from 2015. I pulled this plot actually from a different paper, but anyway. Look at, so these purple curves are the atomic clock sensitivity curves, okay? And I believe this was an actual, so first they proposed it, but then experimentalists were able to actually do this experiment, which is fantastic. And by now, actually, multiple groups have done it. And so these are actual limits they could set already with essentially existing apparatus. I'm plotting here on the y-axis the strength of the coupling. DE, I think, isn't quite GE, but there's some normalization factor, but don't worry about that. And then on the x-axis here, the mass of the dark matter. Okay? So the frequency with which it's oscillating. And then these gray things, those are the current bounds on this coupling. So remember I was telling you in the last lecture they come from new force experiments. EP means equivalence principle here. So for example, they set up these torsion balances in that wash group in Washington, and they measure very precisely, is the equivalence principle obeyed, or is there some new force? Yeah? And we'll talk about that in just a second, but that sets this bound, and as we discussed over there in the last lecture, that's an extremely precise bound. That's a very low coupling, okay? But nevertheless, don't worry about these other lines, okay, for a second. But nevertheless, the atomic clocks can get, this is a few orders of magnitude here, so that's pretty impressive. There's a very big scale on the y-axis. But this is a few orders of magnitude, that's very impressive. Atomic clocks can go a few orders of magnitude past the current bounds. And in fact, as was realized before, look, they get better at low masses, partly a function of that 1 over m that we had there in the amplitude of the effect. You remember that 1 over m? Yes?
Why is it squiggly like that?
Well, anytime you have real data, it looks squiggly. The real answer is you're measuring these two atomic clocks at different, so how do I do this experiment? I run these two atomic clocks relative to each other, then I analyze the data and ask, did they vary? Well, of course they varied because there are Poisson fluctuations, if nothing else, and there are other things too. But what I really want to look for is this common mode, this variation between the two of them at a particular frequency. So, at 10 to the minus 20 EV might be a month or something. So I want to ask, did they vary with respect to each other at a month time scale, or a week time scale, or whatever, right? And when you looked at the real data, there was some noise in it. So the different time scales were all, even two very neighboring bins were slightly different from each other. How much the noise overlapped that band? There's some white noise, and the actual realization of this experiment looked like that, basically. Good. Okay. Yes. It's not quite GE. It's some scaling on GE, and sorry, I've forgotten, but you can check in the paper, and this graph actually comes from my own paper. Not that I did this just because that was the one I had access to, but I don't remember what convention we use for DE. In different papers, I've used so many different conventions I can no longer remember. But I hope we said in that paper what. So the figure actually comes from this paper. Okay, great. So is this clear how you could use atomic clock to look for this?
In this case, this delta n is not a 10 to the minus 30
Yeah, look, this works on the left edge of the parameter space, right? The low frequency regime. When I try to get up, I'm not even plotting to EV here, right? It's hopeless up there. Exactly. That's why you see this 1 over m slope here, right? It's where the effect is biggest that I can see it. Yeah, better. Yeah, atomic clocks are really good. Even paying the suppression of, I had to, this is not the leading order effect in the energy levels. I had to look for the different delta ME scaling of the two levels. So that cost me a few orders. That cost them a few orders of magnitude in this.
I just want to make sure. So we are measuring delta T or delta N.
So this is looking for variations in you're actually measuring the phase observed by the atomic clock, essentially. And well, you're actually measuring something else, but let's pretend you're measuring the phase. So you're measuring the phase, that delta E times T, but you're measuring it separately in these two different atomic clocks. So if you like, one of them defines the T, and then the other one looks to see, did the phase that it sees, did its delta E vary with respect to that? So ultimately, I'm looking for this shifting delta ME. Yeah. Oh, sorry, yeah. Yep, this one is a rubidium and cesium. This one I think is dysprosium. Great question. It's not my experiment. So that's one of those details I couldn't say for sure. But mostly the answer would be yes, as in you need things you can make an atomic clock with. So there aren't that many different elements. Rubidium, cesium are two good ones that they've done historically for a long time, or make something like this with. But also, right, they would have looked for, out of the things that they can use and make fairly precise, what would give them the biggest, what would have the most difference in dependence on ME, exactly. And there will be, by the way, this is not the end. There will be, further follow-ups where you can improve this and things like that. Yeah.
That's the question is, does it keep going that way, or will there be something else?
Keep going which way?
I mean, we're kind of going
to the right.
The cutoff is from the 10 to the minus 19 limitation.
Here, this cutoff? Well, that cutoff is where they chose to stop their analysis. So although it could have been also imposed by things like, but that's a very low frequency, so I don't think it was. In principle, the high energy cutoffs can come from, usually it's where you chose to stop your analysis. Usually you choose to stop it before your experimental apparatus craps out. There is a highest frequency that's easy to measure. That one looks low enough that I suspect it was just where they chose to stop it. I'm sure because they knew they were going to be way above the current bounds.
So how would this improve with improving clocks?
So if you could improve, I mean, it's a somewhat complicated question because it depends on which atoms you're switching to and what dependence the levels have on ME. But in general, absolutely, this is exactly the sort of, this is why we love this kind of high precision technology. It would come down the plane, exactly. Yeah, not move left to right, but come down the plane, exactly. All right, good. Let me see if I think what I wanted to say. All right, excellent. Now, for the same kind of dark matter, there's another sort of signal. Oh, sorry, question?
Yeah, thanks. Are there any anomalies in atomic physics that point to something weird that you might want to like in terms of a light dark matter signal?
Maybe. That could be a bit of a controversial question, so let me not answer it on camera. No, yeah, maybe I'll stick with that answer actually. It's a good question. Maybe let's talk after. I think the real answer is there's always anomalies in experiments, and it can be tricky to know, is this the sort of thing I want to work on right now or not? All right. There's another way to look for dark matter that couples like this, for example. Okay? And that's the following. In fact, you might not be surprised. You see on here these bounds coming from looking for new forces. Those are bounds looking for, as I mentioned in the last lecture, new forces between the standard model particles mediated by these particles. So they have nothing to do with it being dark matter. Those are bounds even on it just being in the Lagrangian, yeah, not being dark matter. These are only bounds on it being dark matter. But they also tell you that these experiments looking for new forces are really precise. They're really good. These torsion pendulums and other things have gotten excellent at looking for new forces. So maybe we can use that technology. Or when I say new, you know what I mean. Yeah, fifth force measurements. Well, let's think about it for a second. So in the last lecture, I told you we're going to treat this dark matter as a perfect homogeneous cosine MT. Yeah, A naught cosine MT. But many of you were already asking, that's not exactly true, of course. It's not dead homogeneous. It's got some spatial variation to it. Okay? So what does that do? Here's my scalar field as a function of position, x. Let's say whatever, it looks like that. It's got some spatial variation, yeah? I won't say how big yet. Well, what happens, so let's say my electron is sitting right here in my lab, and now I don't have a dead homogeneous but fluctuating in time field. I have some slow spatial variation to it. Now, I could ask the same question I asked in the last lecture. Now, what does that look like phenomenologically? What's the electron going to do in response to that? Well, one thing it does, it's mass shifts. We already said that, right? But that just depends on the value of the field right there. So let's say the electron is right here. But, so here, the field has some value, 5 or whatever. So the electron has some mass shift. Over here, the field has some slightly different value, 4.9. So the electron has a slightly smaller mass over here. And over here, it has a slightly bigger mass. So if I put the electron here, what's going to happen? It's like a potential, right? I mean, it is a potential. Over here, the electron has less energy, yeah? It has less mass. So there's a force pushing it that way. Okay? So there's a force proportional to the gradient of this dark matter field. The electron wants to go where it has less mass. Is that clear? So the electron likes to go this way, down the hill. Okay? Now, of course, a split second later, this potential flips sign, remember there is a cosine mt multiplying all of this. So it's an oscillatory force, back and forth, at a very particular frequency. Is that clear? That's great. It's much easier to look for an oscillatory force than a static DC force. That's a good thing to look for. All right. So, so let's say this gives a new force on the electron, and it's different than, so it's, just to be clear, it's not the T-channel exchange diagram that I'm talking about, yeah? This is a new force between standard model particles. This one is. Here, I mean, even if there's just one electron in the middle of nowhere, and it's bathed in this background dark matter field, there is a force on it, right? This is like an electric field or something. It's not mediating a force between some other standard model particle and this electron. No, it's just literally there's a force field, yeah? I mean, a field that is giving a force, at this position. Okay? So the dark matter itself is wiggling the electron. Is that clear? Yeah.
So if you're at very high frequencies, the electron has to travel at some finite speed, right? So would it even have time to travel?
Great, good. And absolutely, all of these measurements looking for the force, for an oscillating force, will suffer as you get to high frequencies. So there will be a high frequency cutoff exactly set by that ultimately I want to see this thing accelerate, but if I don't give it much, even if for the same amplitude force, if I give it less time, it doesn't go as far, 1/2 AT squared. And so from 1/2 AT squared, great question, you immediately know all of these experiments on the right will cut off quadratically. That's the T squared. Okay? we'll see that when we see the plots though. Excellent, good. So what is this force? Or really, what it is the potential, the energy contained in the electron's mass, yeah, is just GE times A, so that's the potential. So this is just the gradient of GEA. Okay? That's the new force. The coupling times the spatial gradient of the dark matter field. That's what you're looking for. All right? Is that clear? Okay, now how big is that? A is not homogeneous. How big are its spatial gradients? Well, remember, your chapter whatever 1 of quantum field theory or something. I always decompose my fields into these Fourier modes, yeah? E to the I omega t minus kx. So you see, the time derivative of a field, that's its energy, right? Time derivatives are energy, right? The spatial derivative, that's its momentum. It's spatial momentum, okay? So this spatial derivative of A, essentially it is the spatial momentum, which is the mass of the dark matter times that velocity of the dark matter, right? And then times A. So this is, so that's what I should plug in for grad A, okay? So now I know how big this force is. So you see I get this force, which is like the coupling times the mass of the dark matter times the virial velocity 10 to the minus 3 times that A. And remember, as we said last time, that this MA is square root of rho, square root of the dark matter density, right? The dark matter density is like m squared A squared. So for this MA, I can just put root rho. So look, isn't that cool? I know how big the force from dark matter is just by the local dark matter density, its local virial velocity, and then of course there's the undetermined coupling. So that's what I'm looking for. Or in other words, the acceleration of the electron is this force over the mass of the electron, of course. In reality, we do this with atoms, so it'd be the mass of the atom or something. Yes? Oh, good. Well, it's whatever local momentum it has here. So this gets back to something we were discussing last lecture. I don't know what local momentum it has here, but let's say I would, unless you come up with some very strange model of dark matter, I would expect that it's essentially not interacting with anything, and so it's just a free virialized particle. And so it has some range, some spread of momentum, but they're all order 10 to the minus 3, basically. Good, yes? All right. Oh, yes, sorry.
A question about force. Why is it a gradient of mass squared
Wait, sorry. Say that again.
Sorry, you write a new force is proportional to GE.
Oh, because the mass is like the energy. So this is like grad U. If the potential was U, then the force is the grad U, right?
Okay.
Like like if I get, if it was a freshman mechanics problem and I give you, here's this potential U of X, find the force on the particle, it's grad of that U.
Is proportional to m squared, right?
M, this is for the fermion. Fermion mass is M side bar side. Yeah, sorry. Yeah, good, thank you. Yes, that's important. Yes, absolutely. Good, yes, other questions? All right. See if I said all this. All right, so that's what we're looking for. Okay. So how can we do it? Just to be clear, so we have some force field around the Earth. I've described it as this scalar field, and then what I could be plotting up there might be this grad A. If I may be in a regime where mass is low enough where the de Broglie wavelength, notice, right? This is the same thing I told you before in a different language. The spatial gradient of this, right, is the scale is set by mv. So 1 over the gradient, that tells you the length scale over which it varies by order 1, yeah? So this length scale is, of course, 1 over this, 1 over mv, which is what we already said. That's the spatial wavelength of the dark matter, the de Broglie wavelength, yeah? So if I'm in a regime where the de Broglie wavelength is long, which we saw in the first lecture, I could easily be in such a regime, then I just have some force field everywhere on the Earth. It's all acting, homogeneously, uniformly, pulling everything, all one way and then all the other way. It's oscillatory in time. By the way, I've been talking so far about scalars. What I'll say in a second is this applies also to vectors too. So I could absolutely have a vector dark matter. It would just have some vev, and it could pull directly. In that case, the direction of the vector tells you the direction of the force. Either way, I can look for this new oscillating force from dark matter. And very importantly, that force, it's some new force, some new field, right? The strength of how much it pulls on this piece of chalk or on a rubidium atom or whatever is determined by the strength of these couplings. This coupling to electrons, in general, if I expect a coupling to electrons, there should also be a coupling to protons and neutrons and whatever else, right? No way those couplings are going to be perfectly aligned to be EP preserving, yeah? In fact, it's really not possible because of binding energies in nuclei and atoms and things like that. So this force will be equivalence principle violating. So 2 different things will drop differently, yeah? That's a great way to look for it because that removes gravity, which is otherwise a mess. So it's a great way to remove backgrounds. So often in these experiments, what we're actually going to look for is a new equivalence principle violating force. Those are some of the most precise experiments we have. Yes?
Would it be possible to see this in a procession of planetary orbits?
Oh, absolutely in principle. So let's say, I'm going to tell you a few ideas, but people have had a bunch of really fun ideas about it. Planetary orbits, effect on binary stars, like double pulsars, things like that. People thought a lot about those things. Let me not say more, but I'll direct you to literature. But also, there may be lots of new good ideas out there. I don't think we're done thinking of ideas for ways to look through this. Absolutely. Yes?
So I'm a little bit confused by how you estimate the force value. So because this axiom is coupled to the electron field, so actually this is a force on the field value, not on the electron.
Well, I'd say we figured out phenomenologically what it did. It shifted the mass of the electron. So now I'm just an electron sitting in this background field, and it has some value. And if the electron is here, it has one mass. But if it moves over here, it has a different mass. So then it really is a force on that one electron. Because it literally, the electron's energy is actually changing as it moves. OK? Maybe we can discuss after. So let me just tell you these. And I see I'm running out of time. So let me tell you these quickly. There's a few. I'm going to tell you a few ideas, although as I was just saying, there's plenty more. One is to use an atom interferometer again. We said they're very precise. I showed you how they measure time. I didn't show you how they measure acceleration, but they do. They're great measures of acceleration. If I have a chance, maybe in the last lecture, I'll show you that. And for example, this is a picture of an experiment built by the Kasevich and Hogan groups in the basement of the Stanford Physics Building. This thing in the middle here is a 10-meter long drop tower where they're dropping 2 different isotopes of rubidium, rubidium-85 and rubidium-87, and seeing if they fall the same. OK? Too many digits. So that's one great way to look for this new equivalence principle violating force. All right? Here's some real data showing the 2 output ports of the atom's wave function. Another good way to look for it. Sorry, I'm doing this very fast. I'm happy to talk more about these. Each of these is sort of a paper in its own right. But, I'm going, or a lecture in its own right. I'm going, I can't spend too much time on each one. But feel free to ask me afterwards. Another thing that happens, is this force is pulling on the whole Earth. So it'll wiggle the Earth with respect to any background frame. Well, what is a good way we have of defining a background frame? Pulsar timing arrays. Okay, if you know about these, what they're doing is there are all these little pulsars all over the galaxy. Pulsars are fantastic clocks. So if the Earth gets dragged a little, this way, so this is, of course, a way people look for gravitational waves for a very similar reason that a gravitational wave also kind of looks like a new force, stretching and squeezing space, so moving how far you are from the pulsars. Also, again, why we're going to use something similar to look for gravitational waves. And again, this is the point I'm going to keep coming back to, that actually looking for ultralight dark matter, looking for gravitational waves, in fact, quite similar, okay, in spirit at least, and sometimes in technique. So this is a gravitational wave detector, but it also makes a great way to look for a new force. So if I'm dragged a little this way, I see Doppler shifts of the pulsars. The ones that are over here get blue shifted, the ones that are over here get red shifted. I can see that because these pulsars are excellent clocks, and I compare them when the pulses come in to an excellent clock, okay? So that's another good way to see this force, this time pulling the whole Earth. By the way, the force is also pulling on all the pulsars, but those are very far away. So we will be able to take them to be out of the coherence length or far enough away that the force on them is order 1 different. Okay, so they're being wiggled too, but they're all being wiggled somewhat differently, and that's not a useful signal. In the pulsar timing, that's degenerate with noise. I don't know the frequency of each pulsar. It has noise in it and things like that. So I want some common mode signal. That would be the dark matter pulling on the whole Earth. Okay, pulling on each pulsar is not so useful for me. Okay, yes?
With the pulsars, I imagine you could also think about something where I think about this pulsar getting slightly heavier through this mechanism and kind of changing the array that way.
Great question. Absolutely. So this is what we've thought of and checked and worked and things like that. But that's absolutely a great idea. So let me say I'm what's the right thing to say? It's a great idea. I've played around with it a little bit. I haven't been able to make it work, but I never like to say no-go theorems. So by all means, really, and I'm not kidding, you're at the edge of research here. People are just coming up with these new ideas recently. It may well be that something like that produces a very interesting idea, for sure. It's possible. By the way, another thing I didn't mention, this is a dark matter coupled to the scalar property like the electron mass. It can also couple to spin, which I'll show you in maybe probably next lecture. And instead of being a new force, that would be a new torque. And that can also be looked for in many of these experiments. And then finally, one fantastic way we have of looking for new forces is these torsion balances. Okay, so you suspend this thing from a string. You have different masses like aluminum and beryllium. And you look to see, is some force you balance it so that if the force is perfectly equivalence principle preserving, there's no net force. But if aluminum and beryllium fall a little bit differently in the force or feel the force a little bit differently, then you get some torquing on this torsion pendulum. Okay, and that, by the way, so we pointed this out to the ETWASH group, and they were excited enough to do an analysis on this. So they've actually already got some preliminary data on that. And let me just point out why these torsion pendulums are so precise. So you have some torsion pendulum here. Ultimately, how did it get to be so precise? I would say one of the reasons is that you read it out. You have this laser readout where you bounce the laser off the torsion pendulum, and then a small shift in angle of the torsion pendulum moves the laser beam, and then I have very good ways to read out a laser. They actually can just really see the spot move. If you wanted to get even more precise, you could do it interferometrically. Right, and see a shift of the laser's angle. Either way, that makes this a very precise machine. I'm glossing over a ton of really important things, like there's lots of noises that they have to spend years and years beating down. Things like fiber thermal noise. The fiber itself, just like LIGO, as you may know, has noise in the supports. thermal noise in the supports. Similarly, there's thermal noise in the fiber that's suspending it, readout noise in the laser. There's all sorts of forces acting on this. You don't even want any tiny grain of dust on it, and you don't want any electromagnetic interaction with any of the housing, and blah, blah, blah. Very hard to do. I encourage you to check out a talk or a paper by the Etwash group. It's a real sort of tour de force measurement, but they've made these things extremely precise. And in fact, I hope you can see from what I've said so far that this measurement technique is actually in many ways rather similar to LIGO. It looks pretty different. I mean, I've been there. It's like a setup sitting on a table. It's about this big or something. You have the laser bouncing off. It doesn't look like a 4-kilometer long device. But I would say to a theorist anyway, they look pretty similar. And indeed, a lot of the noise sources are very similar. They have their laser readout noise, but they also have their thermal noise. They have any of the things that might torque this or twist or act on this macroscopic proof mass. Just as a small note, they've also, over the years, developed another really cool technique where they can spin polarize their masses that they have in the torsion pendulum. So they have net spin. That's easy enough to do. That's like a magnet, yeah? That's how we make a magnet. But we don't want a magnet because this would be then a compass needle, and we know what that measures. That measures any stray magnetic fields at all, really precisely, but I'm not interested in stray magnetic fields, right? So that would be a terrible noise source. No, instead they did something really cool. They built materials where the net magnetic moment, they use two different kinds of materials where the net magnetic moment arises from different proportions of spin and orbital angular momentum of the atoms, of the electrons. If we couple only to the spin, which is what axions do, as I'll show you in a second, not the orbital, then that's great. They align these materials to perfectly cancel out the magnetic moment. So to leading order, this has no response to a magnetic field. But the axion or whatever doesn't see the orbital. It doesn't care about the orbital, only cares about the spin. And so the axion torques this thing order 1. Okay? Anyway, so they can also build these spin polarized torsion pendula and look for spin-dependent forces that way, like with axions. We'll talk about that more next lecture. But so finally, here's some projected sensitivities. So you see again, for example, this is the electron mass coupling I showed you before. This yellow now is these background new force measurements from static EP. This is versus the mass of the dark matter. And you can see our projections for how well you could possibly do with future iterations, improvements to these experiments. And for example, notice this PTA line. These are the pulsar timing arrays. So they're best at these lowest masses or frequencies. These accelerometers, so the blue is the torsion balance and the red is the atom interferometry, can go out to somewhat higher frequencies, but still you see this quadratic cutoff that we were mentioning earlier, because if you go to too high a frequency, the force is jittering the mass too quickly, and you can't see it. Okay? And let me just mention this is for a scalar, but as I mentioned very briefly, and I'll show you more next time, I could, of course, also have vector dark matter. I could have, for example, this is a vector coupled to B minus L, baryon minus lepton number. So under which the standard model is charged directly. So a real, honest to God, new gauge group, new fifth force, but just with a very small G gauge coupling, yeah? So that's a new force too. That can make dark matter too, the exact same way we've been talking about all lecture. That's a new force too, and you can look for it again with these same accelerometers. You notice exactly which experiment is best. Shifts a little bit there, because it has different amounts of equivalence principle violation. And you'll notice here, there's a nice fact that even your gravitational wave detectors like LIGO can start to look for it in the frequency band in which LIGO has sensitivity. Okay, let me stop there because we're over time. But feel free to come up and ask any questions on this, and we'll pick up next time, and I'll talk about other kinds of couplings for light-dark matter.
So anomalies in
Yes?
atomic physics.
Yeah, let me say, there certainly are.
Tear that off. Well,
But
Oh, you have to make